Okay, question 4 of chemical kinetics tutorial. Okay, so in question 4, basically, again, you are given a graphical data. Now, but in question 4, in this case, if you look closely at the data, we are looking at the partial pressure of Cl2 against time. So, what's the main difference between this kind of graph compared with question 3 and question 2? Now, if you notice in this context, Cl2 is a product. Okay, so in this case, this is first time we see product time graph. Whereas in question 2 and 3, what you saw was a reactant time graph. So the main difference between product time graph and reactant time graph is that the concentration of products will increase with time, and that's why you see an upward sloping curve, compared to a reactant time graph which will decrease with time. Alright, because reactants are consumed and products are formed. Alright. Okay, so let's take a look at the context of the question. So decompose to form brown NO2 gas and Cl2 gas. So NO2Cl at the initial pressure is formed this, and then you monitor by monitoring the partial pressure of Cl2. So why can we follow the rate of reaction by monitoring the partial pressure of Cl2? Now this may not be intuitive to many of you. In this case, this reaction you have 2 moles of gas, right? And at the end of the reaction, you have 3 moles of gas. So as a result, you expect pressure, the total pressure of the system, right, to increase with time. Right? Why will the pressure increase with time? Because you have a constant volume, fixed volume. So as you have more moles of gas with time, your pressure of the system will increase. Okay, and this is how we can monitor the partial pressure of Cl2 with time. Okay, so let's look at the question. Let's take a look at A. Using calculation, verify that the partial pressure of Cl2 is 3.20 times 10 to the power minus 2 atm when the reaction is complete. So this is given in the question, 6.40 times 10 to the power minus 2, that's NO2Cl. The reaction is 2NO2Cl to form 2NO2 plus Cl2. Again, given that all of them are gas. So since the mole ratio is 2:1, and given volume is kept constant, pressure is proportional to the number of moles, amount of Cl2 produced will therefore be half the amount of NO2Cl present. Okay, because every 2 moles produces 1 mole. So which means I will have half the amount of NO2Cl, I will have half the amount of Cl2 produced as compared to NO2Cl. So as a result, the partial pressure will also be half of what NO2Cl have. The partial pressure of Cl2 will be half the partial pressure of NO2Cl initially. So half times 6.40 times 10 to the power minus 2, and therefore you get 3.20 times 10 to the power minus 2. Okay, so again, using the mole ratio and given fixed volume, the pressure is therefore proportional to number of moles. Okay? So basically tapping on what you have learned from the gaseous state. Okay, moving on to B part 1. From the graph, determine the order of reaction with respect to NO2Cl and show all working clearly on the graph. Hence, write the rate equation for the thermal decomposition of NO2Cl. So in this case, this is the first time you see a product time graph. I need to run through a concept with you guys. So in this case, let's take a look. We have reactants to products. Okay, at time t equals to 0, assuming this is the first order, first order reaction, you have 100% of the reactants, 0% of products. Okay, so first order, at the first t half, t equals to 1 t half, alright, it will be 50% reactant remaining. You also form 50% of your product. Okay, when it's 2 t half, this becomes 25% of your reactant remaining. And then, how do I get the next one? I will add 25%, because when I subtract 25%, I'll add 25% to my products, and therefore I get 75% of my products. So that's the second t half. At the third t half, after 3 t half, I minus 12.5%, I get, because 12.5 divided by 2, right? You get, 25 divided by 2, you get 12.5%. So I subtract 12.5% from 25 to get 12.5%. Alright, and then I therefore have to add 12.5%. Therefore get 87.5%. And this so goes on so far and so forth. So you can see for your product time graph, you start from 0%, you increase to 50, 75, 87.5, and then with infinitely you reach eventually 100%. Now in this context, because we are monitoring CL2, right? What's 100% of CL2? 100% of CL2 is what you have calculated in A, which is 3.20 times 10 to the power of minus 2 ATM, right? This is what we have proven. When the reaction is complete, your partial pressure of CL2 is 3.20 times 10 to the power minus 2. And this is your 100%. And so far? So, therefore, can calculate out what's 50%, what's 75%, and what's 87.5%. 50% will therefore be 1.60 times 10 to the power of minus 2. Okay, 50%. 75%, second T half. 75% 3/4, right? Will be 2.40. 87.5 after 3 T half will be your third T half. So in other words, we are looking at the time taken from 0 to go to 50, 50 to go to 75, 75 to go to 87.5. So 0 to 50. From here, this point here to this point here. Let's take a look at the time taken. This is the time taken. About 900 seconds. Okay, so you read from the grid, about 900 seconds. Okay, from 50% to 75%, that's a second T half. Right, second T half. Time taken, second T half, right, 75% of 3.2, which is 2.4, 900 seconds again. So you can see it's constant T half. And really just to prove a point, from 2.4 to 2.8, where is the third T half over here, right? Time taken, up to 2700 seconds. You guys can see T half still 900. So you can see that T half is kept constant, and therefore the order of reaction must be equals to 1 with respect to NO2Cl. Okay? So basically, if you understood the explanation, right, at 100% is 3.20 times 10 to the power minus 2, because this is what we've calculated in part 1. Partial pressure of Cl2 will be 3.20 when the reaction is complete. When the reaction is complete, you have 100% products. Okay? So at the first T half, 50% is formed. Okay, so again, why 50%? It's based on this concept over here. Reactant from 100 to 50, there's a decrease in 50, products will increase by 50. Okay? So, half, 50% of 3.2, 1.6. Second T half, it will increase to 75%. Okay, how do I get 75%? Again, products can only increase with time. So, from 50%, you need to add 25%. How do I get this 25%? Because reactants decrease by 25% in the second T half, your products will add 25%. So 50 add 25, you get 75%. Okay, so 75% of the 100% will be therefore be given as 2.4. 0 times 10 to the power minus 2 ATM. Okay, third T half. So third T half from 25% for reactants, it will drop to 12.5 because halving of it, right? So the decrease is 12.5%. The products will therefore add correspondingly 12.5%, you get 87.5%. So 87.5% of 3.2 times 10 to the power minus 2, you get 2.8 times 10 to the power minus 2. And these are the, therefore, what I call the numbers that I will draw on my graph to show my T half constructions. And so far? So once you have these numbers, right? So what I've explained is the numbers that we've gotten. Show your construction lines, label your T half, construction lines, label T half. All we need is just 2 sets, right? 2 sets of T half, because that's the bare minimum to show that half-life is constant. So at least 2 half-life. Okay? So from the graph, T half is constant, and therefore order of reaction with respect to NO2Cl is 1. And therefore, because it's 1, the rate equation is rate equals to K NO2Cl to the power of 1. Okay? So you can either write your rate equation like this, Or you can also write rate equals to K partial pressure of NO2Cl. It's also fine because in this case, it's a gaseous reaction. So you can also express partial pressure in a rate equation. Alright, but it's perfectly fine if you want to keep it in concentration term. Alright, so to calculate rate constant for this reaction, instead it's units. Okay, so this is a first order reaction. So T half equals to ln 2 over K. K equals to ln 2 over T half. Substitute in T half, 900 seconds, and therefore your T half will have, your K will have a units of per second because you're dividing by seconds over here. So K will equals to 7.70 times 10 to the power minus 4 per second. Okay, moving on to part C, explain why the thermal decomposition is not an elementary reaction. So this is a concept that we need to discuss. Elementary reactions are basically single step reaction. So basically, how do I know whether it's a single step reaction? We look at the rate equation. For a single step reaction, the rate equation is based on the stoichiometric equation. Okay, so let's take a look at stoichiometric equation and the rate equation. Okay, the stoichiometric equation is 2Cl to form 2NO2 and Cl2. Okay, so I'm going to write this down. So the stoichiometric equation is 2NO2Cl to form NO2 plus Cl2. Right, 2NO2. Alright. So if this is an elementary reaction, the rate equation, if, I say again, if, big if this is an elementary reaction, rate will be equals to K NO2Cl squared. Okay, if this is elementary because it's based on the stoichiometric equation 2. Alright? The stoichiometric coefficient of NO2Cl. But what we saw was that it's a first order reaction and therefore it's not based on the stoichiometric equation. So this is not an elementary reaction. Okay, because the rate equation is not based on the stoichiometric equation. Okay? So again, you need to understand what they mean by not based on the stoichiometric equation. Okay, and then in part D, we're supposed to propose a mechanism that's consistent with the experiment data. Indicate which step in the mechanism is the rate determining step. Okay, so again, recall your rate law is K NO2Cl. So in the slow step, we always work with the slow step because this is the rate law given. We only have one NO2Cl involved in the slow step, nothing else. Alright, because that's the given by the rate equation. So one, we put it as the reactant, we focus on what's the product. So to think about what's the product, then we need to look at the overall equation. Alright, the overall equation is given as 2NO2Cl to form 2NO2 and Cl2. We try to propose something, the products of the slow step, to contain something that's the product, that's related to the product. So in this case, I can propose the formation of NO2. Why NO2? Because NO2 is the product here. To balance the equation, I will therefore need to propose the presence of what we call an intermediate. How do I know that Cl is an intermediate? Because you can see Cl does not appear in any of the overall equation. Okay, so once I propose an intermediate, remember, put your intermediate in your next step. Alright, because intermediate will be used up. Alright, so intermediate has to be used up, so Cl is used up in step 2. What can react with? So you take a look at this, what's then the next reactant? Then again, take reference from the overall equation. You need 2, right? So far I only use 1, so therefore I react with another NO2Cl. Okay, I react with another NO2Cl, and then to propose the product, I can propose another NO2. Why? Because again, there are 2 NO2. I have 1 so far. I need one more. And then the other product will be your Cl2. Okay? And then you check that everything balances. 1Cl, 1Cl, 2Cl. NO2, 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 Cl, Cl. Last thing to check, two things to check. Your rate law, only one NO2Cl is involved. And when you sum your step 1 and step 2, you get overall equation. So take a look. 1 NO2Cl plus 1 NO2Cl, 2 NO2Cl. This Cl intermediates cancel away. You have 2 NO2 and 1 Cl2. Alright? Okay, 1 Cl2. Okay? Okay, that's part D, not the proposed mechanism. Okay, moving on to E. On the same axis, sketch another graph to show how the partial pressure of Cl2 will change if the initial partial pressure of NO2Cl used is 3.20 times 10 to the power minus 2 atm. Okay, so compared with the earlier example, just now, we start off with 6.40 times 10 to the power minus 2 atm. Okay. Now it's half. Okay, so let's think about it. Should T half remain constant? Okay, T half should remain constant because it's still a first order reaction, right? We recall rate equals to K and O2Cl. So we know that T half remains constant because T half is defined as ln 2 over K. In this case, your K is unaffected by your NO2Cl, right? K is a rate constant, so K is not changed because you're still doing it at the same temperature. You only change the partial pressure of NO2Cl. So T half should remain constant at 900 seconds. And so far? Okay. Now the question is then, how then do we work out the graph? Now, if you use 3.2 times 10 to the power minus 2, the partial pressure of Cl2 at 100% will therefore be equal to 1.60 times 10 to the power minus 2. How do I know that? Because of the mole ratio. 2NO2Cl is to 1Cl2. Right, so this is similar to what we discussed earlier on. So now the 100% is 1.6 times 10 to the power minus 2 at the first T half. At the first T half, 50%, right? So again, remember 100% is now 1.60 times 10 to the power minus 2. 50% will be 0.8 times 10 to the power minus 2. Second T half. Okay, first T half. Second T half. 1,800 seconds. Alright? 900 times 2, right? Will be 75%. 75% of 1.6 will be 1.2. And last point will be your 87.5%. So you get 1.4 times 10 to the power minus 2. Again, another T half. 900 seconds, right? And from these points, that's how I get the sketch over here, right? 0.80, 1.20, and then 1.40, and so forth. Okay. So again, concept learned here, T half should remain constant because T half formula is T half equals to ln 2 over K. When we change the concentration of NO2Cl, remember your rate constant is not affected. Your rate constant is only affected by temperature or your catalyst. Okay? Okay, if not, move on to F. Okay, describe briefly another method other than monitoring change in pressure that can be used to investigate the kinetics of this reaction. Okay, so in this case, you realize in the context of the question, they say that NO2 gas is brown in color. So we can also monitor the change in color intensity of brown NO2 gas. Alright, so we can monitor color intensity, which is proportional to the concentration of NO2 product. Okay. So take note, we cannot accept monitoring change in partial pressure of other gases because they ask for a different method. Okay, also change in volume is not possible because the container given has a fixed volume. So this is the only answer that we accept. Okay, change in color intensity of the reaction mixture against time.